Welcome to this video on a solution to the Basel problem, which is the task of finding the infinite series formed by the reciprocals of the squares of the natural numbers. The solution to this problem was first worked out by Euler himself, but the method that we provide over here to find the solution is different from the method used by Euler. Euler used a method based on a power series expansion of the function sin x at the point 0, and the method that we use here is also analytical in nature, but we use a well-known identity of the cotangent function to place an upper and lower bound on the sum of the reciprocal squares of the natural numbers. Finally, we pass into the limit and then conclude the proof with the help of the squeeze principle. So to kick things off, we start with the statement of the Basel problem and its solution itself. So define the sequence a sub n by 1 upon n squared for all natural numbers n. Then it follows that the series a sub n from n equals 1 to infinity converges, and the value it converges to is pi squared upon 6. A quick corollary to this is the value of the Riemann zeta function evaluated at the point 2 is also pi squared upon 6, because the Riemann zeta function evaluated at the point s is the sum of the terms 1 upon n to the power s as n goes from 1 to infinity. The first key ingredient that will be required in our journey to prove the proposed solution to the Basel problem is the fundamental theorem of algebra. So the statement goes as follows: let n be a natural number, then place p of z to be the sum of a naught plus ai times z to the power I as I goes from 1 to n, where the coefficient on z to the power n is non-zero. Let all the numbers a sub I be complex. Then p of z is a polynomial with complex coefficients and of degree n greater than or equal to 1. Also, the fundamental theorem of algebra asserts that p has exactly n roots, taking multiplicity into account. It is also remarked that if lambda 1 up to lambda n are the n roots of p, where the lambda sub k are not necessarily distinct, then the sum as k goes from 1 to n of lambda sub k equals the negative of the ratio of the coefficient on z to the power n minus 1 to the coefficient on z to the power n. We now state the key identity that is pivotal in bounding the sum of the reciprocals of the squares of the naturals. This identity is based on the function cotangent of theta evaluated at n distinct points. So let capital N be a natural number. The identity states that the sum as little n goes from 1 to capital N of cotangent squared of n pi upon 2n plus 1 equals capital N times 2n minus 1 upon 3. And now for the proof. De Moivre's theorem makes an appearance in the beginning. So if m is a natural number, then we know that cosine theta plus I sine theta raised to the power m equals cosine m theta plus I sine m theta. Here theta can be any real number. Furthermore, if sine theta is non-zero, then it can be factored out from the expression cos theta plus I sine theta to give sine theta times cotangent theta plus I. So combining this with De Moivre's theorem, if sine theta is non-zero, then sine theta raised to the power m times cotangent theta plus I raised to the power m equals cosine m theta plus I sine m theta. This relation we label with an asterisk. We will now begin slowly to mold this expression and then equate the imaginary parts to arrive at our identity. So first, using the binomial theorem, we know that cotangent theta plus I raised to the power m can be expanded as the sum as j goes from 0 to m of I to the power j times m choose j times cotangent of theta raised to the power m minus j. Now if m is taken to be 2 times capital N plus 1, then the imaginary terms in cotangent theta plus I raised to the power m come from all the odd indices of j, that is j equals 1, 3, 5 all the way up to 2n plus 1. So more precisely, the imaginary part of cotangent theta plus I raised to the power 2n plus 1 equals the sum as k goes from 0 to capital N of minus 1 to the power k times 2n plus 1 choose to k plus 1 times cotangent of theta raised to the power 2 times n minus k. So here the index j, since it is odd, is relabeled with the index 2k plus 1 as k goes from 0 to n, and I raised to the power 2k plus 1 equals minus 1 to the power k times I. So that is the reason for the minus 1 to the power k at the front of the expression inside the summand. The binomial coefficient 2n plus 1 choose 2k plus 1 then follows from the fact that j is being labeled as 2k plus 1. And lastly, m minus j, which is 2n plus 1 minus 2k plus 1, gives 2 times n minus k. That is why we have the final quantity cotangent of theta raised to the power 2 times n minus k. Now translating this into a polynomial expression, we see that if we label the sum as k goes from 0 to capital N of minus 1 to the power k times 2n plus 1 choose 2k plus 1 times z to the power n minus k as a polynomial p of z, then p has complex coefficients and is of degree capital N. Furthermore, the imaginary part of cotangent of theta plus I raised to the power 2n plus 1 equals the polynomial p evaluated at the point cotangent squared of theta. So in place of z, we substitute cotangent squared of theta and get an expression for the imaginary part of cotangent of theta plus I raised to the power 2n plus 1. Moreover, we can now equate imaginary parts in the relation asterisk when we take m equal to 2n plus 1, and we obtain p of cotangent squared of theta times sine theta raised to the power 2n plus 1 equals sine of 2n plus 1 theta. Note that the imaginary part on the right hand side of the relation asterisk comes from sine m theta, and here m equals 2n plus 1. P is the polynomial that we had defined earlier, namely the sum as k goes from 0 to n of minus 1 to the power k times 2n plus 1 choose 2k plus 1 times z to the power n minus k. This relation that we have now derived holds true as long as sine theta is not 0 itself. So if we allow little n to range between the values 1 and capital N and set theta equal to little n pi over 2n plus 1, then for all these values of little n, sine theta will never be 0 because n pi upon 2 capital N plus 1 always lies in the open interval 0 to pi upon 2. On the other hand, sine capital 2n plus 1 times theta is always equal to 0 because the factor of capital 2n plus 1 cancels out in the numerator and denominator, and what we're left with is sine n pi, where n ranges between 1 and capital N, and sine n pi is always 0. So for these capital N different values of little n, we see that sine capital 2n plus 1 theta equals 0, and this expression is on the right hand side. On the left hand side, sine theta raised to the power 2n plus 1 is never 0, and so it follows that p evaluated at cotangent squared of theta must be equal to 0 for all the capital N different values of little n. That is, for theta equal to n pi upon 2n plus 1, when n equals 1 all the way up to capital N, we have p of cotangent squared of theta equals 0. As was remarked earlier, n pi upon 2 capital N plus 1 lies in the open interval 0 to pi upon 2, and we also note that the mapping theta to cotangent squared of theta is strictly decreasing on 0 to pi upon 2. So it follows that for all the capital N different values of little n, cotangent squared of theta attains a different value. So each of the capital N different values of cotangent squared of theta are distinct from each other. Also, these capital N values of cotangent squared of theta give rise to capital N roots of the polynomial p of z, and we remember from earlier that p was a polynomial of degree capital N, and so by the fundamental theorem of algebra, it has exactly capital N distinct roots taking into account multiplicity. We have found capital N distinct roots, so there can be no other roots for the polynomial p. In other words, we have found all the roots of p, And now from an earlier remark, we can deduce what the sum of all these roots is. So in the case of p, the coefficient on z to the power n is 2 times capital N plus 1, because we simply take k to be equal to 0 and we get 2n plus 1, choose 1, which is 2n plus 1, and the coefficient on z to the power n minus 1 is negative 2n plus 1, choose 3. So if lambda 1 up to lambda n are the n roots of p, then their sum equals minus a sub n minus 1 upon a sub n, which equals 2n plus 1, choose 3 over 2n plus 1. And when you work out the algebra, it simplifies to capital N times 2n minus 1 upon 3. So finally, this proves the identity that we stated in the beginning. The sum of the n distinct roots, which are cotangent squared of n pi upon 2 capital N plus 1, as little n goes from 1 to capital N, equals capital N times 2n minus 1 upon 3. Here we present the inequality that works in conjunction with the previous identity to bound the series formed by the squares of the reciprocals of the naturals. It states that for theta in the open interval 0 to pi upon 2, we have that sine theta is strictly less than theta, which in turn is strictly less than tangent of theta. We give a geometric proof of this. We consider the arc length of AC and the length of the line segment AB. We know that the length of the arc AC is greater than the length of the line segment AC, which in turn is greater than the length of the line segment AB, since AC forms the hypotenuse of the right angle triangle ABC. But the length of the arc AC equals theta if the radius of the circle equals 1, and in that case the length of the line segment AB equals sine theta. So from the first inequality relating the arc length of AC to the length of the line segment AB, we have that for theta in the open interval 0 to pi upon 2, sine theta is less than theta. To prove the second half of the inequality, we need to consider areas. In particular, we consider the area of the triangle AOD and the circular segment OAC. Since OA equals 1, we know that the tangent of theta, which equals the ratio of the opposite side to the adjacent side, equals AD upon OA. And since OA equals 1, we have that AD equals the tangent of theta. Moreover, the area of triangle OAD equals tangent of theta upon 2, as can be found using the formula that the area of a triangle equals half base times height. In addition, the area of the sector OAC equals theta upon 2. Here we use the formula that the area of a circular segment equals half r square times theta, where theta is the angle subtended by the segment. And so comparing areas, we have that the area of sector OAC is less than the area of triangle AOD, which implies that theta upon 2 is less than tangent theta upon 2, which in turn implies that theta is less than the tangent of theta. Using the identity of the sum of the squares of the cotangent function and the inequality sine theta less than tan theta for theta in the open interval 0 to pi upon 2, we can bound the sum of the squares of the reciprocals of the first n naturals. But in order to draw any conclusions as we pass to the limit, we need something known as the squeeze principle, which is a result from elementary analysis. So its statement goes as follows: let an, bn and cn be three real valued sequences, and suppose that for all natural numbers n, a sub n is strictly less than b sub n, which is strictly less than c sub n, and that the sequences a sub n and c sub n both converge to x as n tends to infinity. Then the squeeze principle states that the sequence b sub n also converges in R to the value x as n tends to infinity. The proof comes in two parts. For the first part, we show that for every positive epsilon, there exists a point capital N such that for all little n greater than or equal to capital N, we have that the gap between a sub n and c sub n is less than epsilon. Note that a sub n minus c sub n is always strictly positive, since a sub n is always strictly greater than c sub n. To prove this first half, we know that there exist natural numbers capital N1 and capital N2 such that for n greater than or equal to capital N1, we have that the modulus of a sub n minus x is less than epsilon upon 2, and for n greater than or equal to capital N2, we have that the modulus of c sub n minus x is also less than epsilon upon 2. This is since the sequences a sub n and c sub n both converge to x. So define capital N to be the maximum of capital N1 and capital N2. Then for all little n greater than or equal to capital N, we have that the difference a sub n minus c sub n equals a sub n minus x plus x minus c sub n, which is bounded above by the sum of the modulus of a sub n minus x and the modulus of c sub n minus x, which in turn are both strictly less than epsilon upon 2. And the sum of two lots of epsilon upon 2 gives epsilon. So it follows that a sub n minus c sub n is strictly less than epsilon, and this can always be achieved for every positive epsilon. Now in the second part of the proof, we use what was established in the first half to prove that b sub n also converges to x. So choose capital N sub 3 so that for n greater than or equal to n sub 3, we have a sub n minus c sub n is strictly less than epsilon upon 2. This is possible by what we just proved. Now recalling that capital N1 was chosen so that for all little n greater than or equal to capital N1, we have that the modulus of a sub n minus x is strictly less than epsilon upon 2. We set capital N this time to be equal to the maximum of capital N1 and capital N3. And then for little n greater than or equal to capital N, we have the modulus of x minus b sub n is bounded above using the triangle inequality by the sum of the modulus of x minus a sub n and the modulus of a sub n minus b sub n. Now the modulus of a sub n minus b sub n is strictly less than a sub n minus c sub n, and by the way capital N has been defined. Both the quantities, the modulus of x minus a sub n and a sub n minus c sub n, are strictly less than epsilon upon 2, which again sum to epsilon. So it follows that the modulus of x minus b sub n is strictly less than epsilon, and so the sequence b sub n converges to x as well, thereby proving the squeeze principle. After having spent a long time in laying down the necessary prerequisites, we finally come to the proof of the fact that the infinite series formed by the reciprocals of the squares of the naturals in increasing order is pi squared on 6. We know that whenever s is greater than 1, the series 1 upon n to the power s as n goes from 1 to infinity converges, and so the series under consideration where s equals 2 also converges. Now to prove equality to the limit that we have stated, we start with the inequality sin theta strictly less than theta strictly less than tan theta for theta in the open interval 0 to pi on 2. On squaring and taking multiplicative inverses, we have that the cotangent squared of theta is strictly less than 1 upon theta squared, which in turn is strictly less than the cosecant squared of theta. And from a familiar trigonometric identity, we know that the cosecant squared of theta is nothing but 1 plus cotangent of theta squared. This result we label with an asterisk. Now, if we set theta sub n equal to little n pi over 2 capital N plus 1 for n equal to 1 all the way up to capital N, then theta sub little n always lies in the open interval 0 to pi on 2. Hence the inequality is asterisk hold for n equal to 1 up to capital N, where theta is substituted by theta sub n. Now if we take the sum as little n ranges from 1 to capital N, then we have that the sum of cotangent squared of n pi upon 2 capital N plus 1 as n goes from 1 to capital N is strictly less than the sum as n goes from 1 to capital N of capital 2n plus 1 over n pi all squared, which in turn is strictly less than capital N plus the sum as n goes from 1 to capital N of cotangent squared of n pi upon 2n plus 1. Now using the identity we proved earlier, the quantity on the extreme left is capital N times 2n minus 1 upon 3. This is strictly less than 2n plus 1 upon pi all squared times the sum of the reciprocals of the squares of the naturals as n goes from 1 to capital N, which is in turn less than capital N plus n times 2n minus 1 upon 3. Furthermore, multiplying all sides of the inequality by the quantity pi squared upon 2n plus 1 all squared, we have that pi squared upon 3 times n into 2n minus 1 upon 2n plus 1 squared is less than the sum of 1 upon n squared as n goes from 1 to capital N, which in turn is less than pi squared upon 3 times 2n times n plus 1 upon 2n plus 1 all squared. And finally, taking the limit as capital N goes to infinity and using the squeeze principle, we have that the sum of 1 upon n squared as n goes from 1 to infinity equals pi squared upon 6, thus completing the proof. Some useful references and sources for further reading are the books by John and Howie called Real Analysis and Ivan Niven et al. Called An Introduction to the Theory of Numbers. The first is published by Springer and the second by Wiley, and they are both excellent sources.